Welcome back, everyone. So today it's again just me and Marinho.
Hello.
So now that after this brief introduction, Lemos is not with us today. He's traveling to somewhere, so it's basically gonna be just us for a few. I think just next week, right? Lemos is coming back next week, I think.
Yeah, I think that's right, actually.
All right. So by the time I think we upload this, he might be back already. So anyway, we let's just to recap now where we stopped. Last session we basically increased the amount of opcodes we have, and I don't think I can share it for you again.
You're not.
Yes, sir. I will do that. Where's this? Where is this? Here we go. Can you see? Oh,
I
hey,
can
can
see.
you see?
Yes,
Okay.
I can see.
So last time we did, I think we did all of these together, if I'm not mistaken, right?
Yes, we
Uh,
did.
yeah, we did low day with the arithmetic. Okay. So we have already implemented, but I think one of the decisions we made was to just go with this for now, but also try to make more high level instructions, right? Instead of using, for example, not having division and multiplication, like arbitrary multiplication, we would try to make more high level instructions, right?
Yeah,
And
because right now we're just following that paper, the second generation stack computer architecture is the
mhm,
title, if I'm not mistaken.
which
That's
is
a
pinned
good
by the
starting
README, by the
point,
way.
but for Chime, since it's meant to be a VM for a higher level language, there's nothing stopping us from having higher level opcodes. It's just we're starting from something more well known and documented first before we experiment.
Yeah.
That is the thing.
Mm-hmm. So I think for now we can keep it the way it is. Um, we're just gonna suffer a little bit writing like code, right? That takes into account like multiplication. So maybe we can write something very simple first, just a test, right? And then later on we
Yeah.
can just rewrite. That shouldn't be right that complicated, hopefully.
Probably not.
Okay, so where is the progression? What else is lacking? Follow according to the paper.
There are a couple instructions missing, mostly the other load and store instructions. Like we have just
Right.
load and store from the A register
Mm-hmm.
to manipulate memory, and also the fetch to grab literal data.
Mm-hmm.
But there are other instructions that are like for more useful in loops, like load with increment and loading and storing based on the top of the return stack in case we need more than one index into memory at the same time. We can have two, no problem. So those are missing. And currently, this is something Magetta asked me to do after last session. There's
Oh,
a
right.
PR open on Chime that adds a document with the missing instructions and also a few others that I started doing. And basically, uh, I don't have
Right, I can
all of
see.
the instructions, but all of the missing instructions are there. So,
So let's see. We
and
have
another, yeah,
documents, missing instructions. That's
and
nice.
another thing that we're missing is actually the instruction stack optimization. That's an important one because if we start writing higher level code, so like more calls and less lower level instructions, we kind of need that to keep the code compact. Otherwise, um, otherwise there's not much point to doing a stack machine at all.
Yeah, makes sense. Let me just give me a tiny fraction of a second. Well, maybe not
Okay.
that little.
And to implement the instruction stack, we have to change the call and return instructions, and also the to and from return stack op instructions as well, um, which are called, I think they are pop R and push R in our implementation.
Pop R
if
and
I'm
push
not
R,
mistaken.
yes. Yes, they are.
It's basically add another stack whenever we call a function. Instead of discarding the instruction register, we push it to the instruction stack. And then when we return, on top of popping the return address into the program counter, we also pop the instruction stack back into the instruction register. So this way, we don't discard the rest of the instructions in the word when we do a call. We can continue executing the same word afterwards when we
Mm-hmm.
return.
Okay. Got it. So let me see your PR here and see what we. Okay, so you made it in an org file, right? I like that.
Yes, it's an org file. I tend to prefer Markdown when I'm just writing for myself because I use Kakone instead of Emacs. But since you were using Emacs and you're kind of the captain of this particular ship, I decided let's go with org
Captain.
mode. It's
Surely I am the captain. Well, I'm not dictating rules here though, so you feel free, man. Like,
yeah,
oh,
no, the navigator,
we don't have a knob. I just noticed.
yeah, we don't. That's one of the missing instructions is the NOP.
So let
Um,
me add it here. Well, the knob would be neutral, right? Instruction. I don't know what would put it here, but
I put it together with, yeah, actually, I put it in an other category because in the paper it's categorized by itself, basically.
mm-hmm.
There's the NOP, and then there are three undefined opcodes that the paper doesn't define for the architecture. They are all in a separate category. So like there's control flow, there's memory access, stack manipulation, arithmetic, and others.
Let me put other. I think that's fine. So what I'm looking here is that you have documented everything we already have, right?
Not quite everything. I documented what we were missing, and then I documented what needs to change for the instruction stack.
Wait, what we're missing?
What we're missing is basically a bunch of load and stores that do other stuff besides just loading and
Let me
storing.
open the
They are
file in the view file. That's better. There we go. So let's see.
probably
We
better.
have the jump, which we do have,
Uh,
right? Jump 0 and jump plus, jump. Stack manipulation, push R.
yeah, and then
We do have push R's, pop R.
those two are the ones that have to change for the instruction stack to work. You will notice that they do something more than just what they currently do in our implementation, if you look at the description.
Oh, wait a
Um,
second. Yeah.
and by the way, the window you're using to look at the file is not on your screen that you're
Oh,
sharing.
because I have work stuff on the background, so
Oh,
I
that's
need to
fair.
just share the screen. I mean, can share for you, but the problem is the stream, right?
No, that's fine. That's fine. I'm just letting you know.
Okay, let me just take a read then. Let's see. So we do. Okay, I suppose you didn't put the load A, but that's okay. So, oh, you have load A plus and store A plus.
Yeah, they load the value from the address, but they also increment the register. So
Oh, right.
if you're reading in a loop, for instance, this allows you to easily
Mm-hmm.
read a lot of data from memory, like an array or something.
Makes sense. And let's see, the load R, load the value from the memory address on the top of the return stack, push the loaded value into the data stack, increment that top of the return stack. Okay,
Yeah,
so
this is
let's
in
just
case
add
you need
those.
yeah, the load and store to DR. They're basically, if you need a secondary index, like if you're already using A for something and you need to iterate over an array,
Mm-hmm.
you can put it, you can push the address of the array on the return stack and iterate from there, basically. It's just a secondary, it's kind of like having a secondary A register just for array manipulation, essentially.
Okay, so something like this, right?
Yeah, something like that. And then if I just go over the documents very quickly. Yeah, I think the only instructions I added to the documents that we are not missing and we don't have to change are halt, which I added because it's not in the paper.
Mm-hmm.
And then the fetch and jump instructions, because I was basically practicing writing the instruction descriptions. They helped me make the rest of the
Oh,
instructions
okay. Mm-hmm.
more clear.
Okay. By the
But
way,
yeah,
I think we should make a folder if you can move later for a like a documentation folder in the root. I think it's better because we can
uh,
even host in like GitHub pages or something later.
I'm sure I can do that. I'll probably also take the opportunity.
Marinho, I think you chopped or you dropped. I'm not sure. Let me pause this. Just give me a sec.
So yeah, just to
So
finish what I was
resume.
saying, I can move the documents to a folder, no problem. I'll probably also take the opportunity and complete the document.
Mm-hmm.
We have all instructions documented. I think that would be nice um, for reference to our future selves or for any other people who decides to participate in the project. I think it's just generally useful to have.
Yeah, I agree. Okay, so let's start copying this. I think we're gonna need three only, if I'm not mistaken. No, three, four, I think five. One, two, three, four, five. And then uh, here we're gonna do op push. Um, no, load, right? I don't think we have the
Load.
load a plus. Yeah, ready?
We have load A, not load A
Yeah,
plus
that's what
yet.
I just added, right? Yeah.
Yes.
So
Load
load
A
a
plus
plus, store a plus, and the same for
uh,
R.
or R. Yes. Uh,
Okay.
and then the
Not
last one is the NOP, I think.
okay. Just let me stretch a bit. By the
The
way, we
NOP
need
is
to
very.
go on.
Oh, go ahead.
I was just gonna say we need to make this work on like VS Code so we can do live share. Doing this is
Yeah, that would probably help.
I don't
Um,
want to rely on Apple for this. Uh,
Apple is a null. We don't rely on nulls.
yes, precisely that.
The NOP instruction is very easy. We can just have nothing and it's done.
Just literally this. Oh, I don't even need this, do we?
I I guess we can log that we went through a NOP just for to make sure it's going to the right branch.
Yeah. Um. Okay. So this a plus. Okay, this function doesn't exist. That makes sense. Oops. Store R. Okay. Mm-mm.
Uh,
Now we
right.
just need to implement those.
Yes.
Where were
They will need
instructions? I believe.
they will need the data stack um, and either the registers or the load and store A plus or the return stack for load and store R plus. And they both need memory. They need access to RAM.
Okay, so can you say it again? What do we need?
Load A plus, it needs the registers, it needs the data stack and the RAM.
So wait, the registers, the data
Yes,
stack,
the data stack
Okay.
And RAM. It needs RAM as well because it's where it's reading from.
Okay. I don't know why I'm putting like underscores here. I suppose the store the same
Is the same, yes.
and the same for here, I think, but
They need the return stack instead of the
instead of the
registers.
instead of the registers.
One thing that Lemos suggested over chat during the week was that we could probably turn those functions into methods of the VM.
We could, yes. Not sure if I want
Um,
to do that though, but we can.
in any case, let's not do that right now.
Yeah, this kind of stuff I think we can leave it for later. It's a problem for us of the future. Where was I implementing this? Do you recall? I don't see it in the instructions
Uh,
file.
Header instructions. It might be in the utilities, but I could be wrong.
Well, that would be terrible.
No, it's not.
I think it's just not showing here. Let me.
Let me check as well.
Oh, we do have the file. It's just not showing here. Okay, now it is.
Oh, good.
Weird.
That's yes, it is weird.
Okay. First stop.
We can probably just copy the body from the load and store A that we already have. The only thing they have to do extra
Is
is
incremental.
increment the register.
Mm-hmm. Just add some spacing here. Oh, I forgot it's not in functions. It's like here. Okay, this is terrible. Store A. Wait. Oh,
It is actually in functions,
Oh, okay.
apparently.
It is indeed. That is the store, right? Yes.
It is.
Okay. And the
Load A.
load. Yes. Danke. There we go. Right.
So
So
itashimashite.
thank you. Okay, so what we're doing here, we're getting the value of A, and then we do get the object at the index, and then now we need to increment on the
The Yeah, we have to set the I forgot the method
registers, right?
to write to the dictionary, but we have to write
Yeah, on the register, right?
on the register A, we have to write A plus one, basically. Uh,
I think it was this. Let me
yes,
pick.
set object A plus one, value of A plus one, actually.
Mm-hmm. Value of A plus one.
For key A. That should do the trick,
Hopefully.
hopefully.
Hopefully. And then we are gonna copy this. Oh, a B. I'm
That's
crazy.
load R. That's load R actually. It's a bit different because we have to grab the value from the return stack instead of the registers. It has to. We have
Oh,
to
right.
do a. We have to do a
Yeah, that's
pop
on the stack, right?
and then a push. I think.
So we need to pop the value, increment, and then push the value again.
Yes, that is
Return,
correct.
return stack, pop, just this. But this gives us,
And then we have to grab the integer value. I think.
yes, we do. There we go. And then here it's not this, it's pull, pop, push, right? By the way, we have a
Uh,
serious issue with if we if we try to do this parallel in the future
what issue?
of concurrency access. We're gonna have to deal with semaphores here probably.
Oh, yeah, the architecture in the paper is it's a single-threaded machine because it's meant to be comparable to a very simple RISC instruction set.
Mm-hmm.
And the simplest instruction set you can come up with has no concurrency primitives, so this one doesn't have them either.
Right. Because I'm thinking here, like, if we. Okay, I think what you're talking about is something different then. Because you're basically saying about the code, right? Executing things in parallel. But I meant the actual, like, the abstraction of the code, not the actual. I think both overlap though. Because
They
here's what I'm
do.
thinking, like, just accessing things, like, imagine like this: we pop and then we push, right? This needs to be atomic because actually needs to be coordinated because you may pop something that you don't want, right? When you call this.
Yeah, the way to model this, uh, like in the actual architecture, generally speaking, you can think of the values in the stacks as being thread local. I'm not sure how we would implement something like that. I mean, it's obviously easier for us because we're doing this in software, not hardware, but
Mhm.
yeah, that's something we will have to think about a little bit. Yeah, I didn't catch that. That's a nice observation.
Okay, so for now, we're gonna have to leave it that. So let's just continue. So I increment, I push back. Now the store. Okay, now
We
the
just
store.
the stars are basically the same. We just had to
So
have
just add back. Mm-hmm. And then on
increments.
the R, we cannot use this, right?
Yeah. Uh, yeah, we have to pop the return stack, and then read the
Oops, I forgot
value.
the
Oh, integer.
integer.
Yeah, we have to do integer value first.
Uh, let's do it on
We
the same order.
read, and then we push back. And that should be it for those instructions.
Well, it's not really value of A at this point, right? Value of R.
Right, it's actually the value of R.
Not that it matters that much, but yeah. Let's name variables consistently. And what's your problem? Oh,
+1, and it's missing a semicolon.
yeah, sir. Okay, so does it build? That is the question we ought to make. Quack, 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 quack.
Oh, right, because the call sites are based on the thing that only reads the data stack. We have to pass
Yes,
the other
sir.
arguments.
So what was the order again? Let me put it here.
It's either the registers or the return stack, then the data stack, and then the memory.
So the registers, right?
Registers, yes.
Then
And then
wait, this is
I,
the plus star. I'm on the wrong one.
yeah,
It's
it's
this
on below. Registers,
data stack
then
and
data
RAM.
stack is correct, and RAM.
What?
I think it's actually called something else. It might be memory or
Memory
something.
RAM. Okay, let's go with that.
It's kind of redundant to call it memory RAM, but whatever. It's already done.
Yes. Well, I mean, the M already means that, right? But
Yes. Uh,
uh,
then load. and store to R are basically the same. You just replace the
Just replace the
registers with
registers. Yes.
yes with the return stack.
Wait, wait. Load store. Load
Load
store.
store. That has to be a store.
So this we pass the return stack. Return stack and the return stack too. Okay, does it build now? Oh no.
It does.
It does.
How fun.
That makes me very surprised actually. That we're not getting like null pointers. Okay, although we're barely using them, right? To just the Objective C stuff. Okay,
Yeah.
so okay, what else now should we do?
Probably the instruction stack first, because before we get caught up in doing other stuff, and that will finish the architecture in the paper,
Right, and then we
and
can
then we
start
can move
doing the
on.
parser and writing and doing more high level instructions, I suppose, and like
Yes,
system
we can
calls
move
and
on
such.
to yeah to other things like yeah system calls. Having a syntax to write the code would be very nice instead of
Mm-hmm.
writing it as an array in Objective C. That would be very awkward very quickly.
Yes.
Uh,
Okay, so what did you suggest? Can you say it again?
Yes. So if you go to the VM, we have two stacks currently, the data stack and the return stack.
Let's go on the here. Right.
We would have a third stack called the instruction stack alongside them.
Okay.
And then we would have to change our instructions. I think the two that are the simplest ones are the push R and pop R, if I'm not mistaken, which they move values from the data stack to the return stack. Um, they have to they have to when you push a value from the data stack to the return stack, you have to also push a zero into the instruction stack to to keep the invariant that the instruction and return stack always have the same depth, the same number of elements.
Oh, I see.
And and likewise, the when we pop the return stack, we should also discard the value on the top of the instruction stack again to keep them the same height.
Okay, so those are additional things we need to add on the instructions.
Yes, and I think those two instructions are actually in line in the big switch over in the VM. So
But what should we add? Just no?
no, we can just push a zero. Like um,
Here's the
it's an
question
arbitrary
though.
value.
How do you know if it's permissible? I think maybe that's not the job of this thing, right? But it doesn't know then how if it's a permissible action to pop or continue popping, right, or not? Because, like, for
Uh,
example, if it's full of zeros, it will never fail, but will still spit a number, right, which happens to be zero.
Yes, but zero is actually the right number for this particular register because remember the zero instruction, the zero opcode means
All
fetch
right,
the
you're
next
talking about
word.
the instruction data stack specifically.
Yes, the instruction data stack, exactly. Uh, it's it's safe to push a zero there because it just means fetch the value of the next words and then we can start executing the instructions afterwards. For dynamic calls, that's the correct behavior because you are pushing a function address into the return stack and then returning into it. And the first thing you have to do when you call a function is fetch the first group of instructions, which zero does. So that's right.
So wait a second, like this is not specific. This is broadly speaking to any instruction, right? That you're saying.
Yes, it is broadly speaking.
So that should be on the loop alongside the switch, no?
No, actually, this is for the specifically when we do the load and push R instructions because they manipulate the return stack.
All right.
And the instruction stack has
The
to
other
be the
here, yeah,
same as
modify. That's
the
right.
return stack. Oh,
Yeah, okay. So on this here, right? You mean? So okay, on the load A, we already have to do it, right?
no, not on load A. It's on push R and pop R, I think are the instruction names, if I'm
So
not
oh, okay, they
mistaken.
are right. It's the return stack.
But we were implementing that's one of the those are two of the instructions that were implemented in line, like before we had this new file with
Yeah.
instructions. So uh, no, it's not load, it's the push and pop R
Right.
instead.
Pop R. Right.
All right, so let's see. Pop R, it pops the return stack and pushes it to the data stack. So we have to add another line to that try block. After we pop the return stack, we also have to pop the instruction stack. And we don't care about the value. We're just getting rid of it.
Okay. So on the data stack.
The instruction stack, the new stack that we
Man,
are
yeah.
adding.
Sorry. Yeah. I was going crazy. Okay, this, and let's copy this because they're gonna repeat, right?
Uh, kind of, yeah. Uh, and now the push R, we have to push a 0. Yeah, push R, it takes a value from the data stack and pushes it to the return stack. We also have to push a 0 into the instruction stack.
We also have to do what? Sorry.
You push a 0 to the instruction stack. You already did it. You already just did that, so it's correct.
Yeah, but is there anything else?
Uh, no. And then the other two instructions, and these ones are a bit less trivial, are the call and return instructions. They now have to.
Mm.
Let's do the call instruction first. So uh,
Oh, okay. Let's
when
go with
we
the call.
do yes, when we do a call, what we do is uh, we have the PC. We push the PC to the return stack. And then after we do that, we also have to push the ISR into the instruction stack.
Right. Okay. So after this push here,
After this push, we have to push the value of the ISR into the instruction stack, which
do we
is
have
not.
that? It's just the opcode, right?
I think it might be somewhere in the loop. It's not the opcode actually, because the opcode is the opcode we're currently executing. We don't care about that
All right.
because we already know that's a call.
Yeah,
Uh,
makes sense. It's
we
the
care about
next
what
one.
comes afterwards.
We do this.
We have to, yes, it's after the shift. So we have to read the ISR register inside of the instruction, I think.
Hmm.
No, actually, we can just take the opcodes plural. That should be correct as well.
This is not available on that scope though.
It's not.
Yeah, we need to make that available.
Well, if it's not available, we can just grab it from the ISR. It should be correct because we store it right before.
So here, and then we do. Oh, thankfully it will be simple because we just do this. So
Registers,
registers, and then I get the object for key and
ISR.
ISR.
Oh, that's That's surprisingly straightforward.
I'm
That's
I'm kinda scared of one thing though.
what?
We're sharing pointers, right? Here. And we do this in
Yes,
a lot
sure.
of places. I think it's
We
fine.
it's kind of unavoidable doing that inside of the dispatching loop of a VM. It's kind of the way it is.
Yeah, just saying because in this, I'm just thinking if there might be a problem doing this because, uh, like, so you're propagating some piece of memory that you mishandle it, because you expect it to have this behavior, but it has another. But I don't think so. I don't think it will be a problem. Okay,
I
so
mean, they're just numbers, so I don't think there's much that can go wrong, even if there is a problem.
I mean, like, you modify in one place the reference of something that was already referencing in another place, and then modifying one of those modifies both. You see?
If you're worried about that, we can always just take the integer value and
Yeah,
then
that's what I
put
thought,
it.
but I don't think that will happen, like the duplication. But let's see. So the next is the
Sure.
ret.
Yes, it's the rats. Um,
Okay, so here.
it has to, right, it pops the return stack and then it has to also, it has to do two things. It has to pop the instruction stack and then it has to write that value to the ISR.
From the registers, right?
Yes, from the registers.
I need. No,
Um,
wait. From the return stack. I wait. I what I need to write
no,
here
we have to pop the value from the instruction stack.
from the instruction, right? So instruction stack pop, and then here for the key
ISR.
ISR. And I don't know why it's doing this, but I hate it. Stop. Okay. That also is straightforward.
Yes, it is. And now we can have lots of call instructions in the same instruction block, in the same word, and that will just work, I think,
So let's
if
try
we did it
writing a
correctly.
program. Shallow one. And I gotta think of the instructions though. There's a place here. We're just putting halt. So what do you suggest?
Uh, Let me look at the paper. I think
Example?
there's a very short program that we can use as an example there.
Okay.
So let's paper.
While you do that, I'll be right back. I'll just go to the bathroom.
Right.
I'm back.
Hello, I found the program in the paper.
Okay.
Um,
By the way, how should I structure this though? It should be an array with elements of six size of other arrays, right? How are we
what?
structuring this? Because right now our opcodes that we just spec We just send one word, right? So
Um, we can just keep adding objects to the RAM,
like
and that
in
should work, I
series,
think.
right? Yeah, makes sense.
Right, so the program is slightly unusual. Normally, when we write example code, it's usually something like, especially in functional context, right? It's usually something like Fibonacci or factorial or
Yes.
whatever. The paper actually uses the triangular numbers as an example. I don't know why, but it does.
Okay.
Um,
Maybe it's just too fast.
but that's hmm,
I would do that. Why not?
but
If you
that's
think of assembly.
that's a bit, I don't know. Because what we actually need to test is multiple calls in a row, right? So actually, it's
Yeah.
probably better to do something like, oh, here, there's an example here. Add two is just,
While you do that, ah, let me see one thing here. How can I edit the git ignore on this thing?
right, so something like this. I'm going to write in the chat and then you can look at it. Um,
I don't think it's catchy on OBS. It's not.
it's not, but that's fine.
There you go. Just gotta add this on our. Uh, what's the name of this file?
So I'm going to write it as an array of arrays in the chat, just so we can have it clearly separated, but
Mm-hmm.
um, let's see. The first word is gonna be the entry point, which is address 0. So we have to do all and then halt, and then we can just fill it with zeros. 1, 2, 3, 4, 5, 6.
What?
And then the second word is going to be the number. I'm basically hand assembling the code. It's kind of silly. I'm just going to put a placeholder here for now. Then the word after that is going to be, I think the instructions are called add, and then return
Oh no, I should not add this. Because this is the thing that binds the director for me.
0. That's 1. That's 2. Then the other function, this is the one we actually want to call. So that's the address 0, 1, 2, 3 is all all let's do call jump actually, proper tail calls because they are important for some reason. Then 0, 1, 2, and then 2. And this should be it, I think. So basically what I wrote is the entry point, which is at address 0. It just calls the function at address 3.
Mm-hmm.
Oh, wait, but this doesn't quite work because we're not setting up the parameters. That's important, right?
Let me see. Call halt and then nop nop nop.
That's not NOP actually. It's the zero opcodes, which I think is
Oh,
called
fetch.
fetch.
Yes, PC fetch. No, wait. We may confirm, but yes, that is
Let me
PC
actually
fetch.
spell out that it's a PC fetch because it's less
No, no,
confusing.
yeah, that's fine. I thought, but here's
And
the thing:
then I
you're
think
gonna call what on that? I don't get it because you're popping. Oh, okay. You read it like below. Oh, never mind. So,
I'm reading it word by word, and then I forgot to pass some parameters to the function, so I'm editing the
but here's
code
the thing,
snippet to
it's
do that.
inverted, no?
No, it's not. Let's see the
Because the
parameters. Let's
chew, like the
do
chew on the background, just for reference for people can see. I'm pasting here.
moment. There we go. I just edited the code.
I copied it.
Copy that. Yes.
So here.
Yes.
So
So
you are
the first.
pushing this first, right? So this is on the bottom
Uh,
of the stack because you came first.
no, I'm actually writing it as it would appear in memory. So like the first item is address 0 basically, and then address 1, 2, 3, and so on.
Okay, so it is in series.
It
But
is.
then
Then the first word is actually a series of instructions, which is call, halt, and then we just fill up the rest with zeros, which is PC fetch because that's what you do. But yeah, we should call the function at address 3 and then halt. And then at address 2, we have a helper function that just adds two numbers and returns. And then at address 3, which is the function we're actually calling, it has three
oh, I see.
fetches, then a call and a jump. Uh,
Mm-hmm.
so the way it
I
works
see. I
is
see.
that it's going
I
to,
understood now. I think.
so it's going to fetch the next word. So it's going to put a 3 on the stack. Then it's
Mm-hmm.
going to fetch again, which is going to put the 4 on the stack. And then a third time, which will put the 5 on the stack, and the 5 will be on top and the 3 on the bottom.
Right.
Then we call address 2, which is that helper function that just adds two numbers. And then we jump to address 2, which also adds two more numbers. And
Mm-hmm.
then that's the end of the program. So it's going to return, and then it's going to halt, basically.
Okay, so
And
help
there's
me out here.
and
So
at the end of all this, there should be a 12 on top of the stack.
so let's go back here. I think I got it. So in this case here, it should be. We're gonna need to pack the first word. It's gonna be a OP call,
And then an OP halt.
and
And
then
then I
a
just put
PC
a fetch
fetch.
there because it's what we usually use to fill up the rest of the words, but you can put whatever because it's gonna halt anyways.
Yeah, I'll just put the PC fetch on 0. Okay, so I. So let me do a dirty thing. Okay, you are not seeing this. There.
That
Oh,
works actually.
I can't do that though.
Well, no,
Let's
you
see.
can't because C doesn't have array literals in the traditional sense.
Ah, yes. So word 1, I guess.
It's word 0 because it's
Yeah.
address 0 in memory. So
Okay. Word 0. Then the
then we
second
have
will be.
word 2 because the others are just numeric constants.
No, but wait. They're constants. Oh, I see. You're just showing because here's the thing. Like 3, we still have to.
We just have to. It's just a number, the number 3, like the actual number. It's technically a memory address in the machine's RAM. It's going to be interpreted as an address, as an index into RAM,
But
but it's the
okay,
address
so we
number
need to
3
put it
because
as hexadecimal then, right? Because
I
if you
mean we
put as a
could.
normal integer, isn't that a normal opcode like in a word? Like 3 will match with, I don't know, who is 3? 0, 1, 2, 3. It will map with this on the switch. I mean,
Well, no, actually, because that's the thing. When we decode an instruction, we start from the high bits, so technically it would be a fetch, actually.
I see.
But it's not going to be treated as an instruction anyways, because when we do a call, we read the next value, right, from
Mm-hmm.
memory, and then we increment the program counter, so we skip that value when we continue execution.
Okay, makes sense. So I can just ignore them, right, on here.
You can, yeah,
So
you can think of it this way. You know how opcodes they can have operands. In a stack machine, the operand is literally the word after it. But because we are packing many opcodes in
mm,
a single word can have up to 6 arguments
yeah, I
if
see.
all of the words
Yeah,
take an
okay.
argument.
That's not what I was not thinking. Like makes sense. It is reference I need to think of referencing the opcodes in a word, not a one thing as you would put in a stack, right? Normally.
Yes, exactly. So it's
Okay.
op. I think it's called op plus actually. I wrote add because it's the
Mm-hmm.
name used in the example, but it's actually plus.
This I guess.
Uh, it is. And then word three is three fetches, not the PC fetch, just a regular fetch. And then we do a call and a jump. And that's the end of the word.
Okay. So let's just do this. Copy paste. 2 and 3. This.
Yes. And then in between those, we have to also add the numeric constants.
Mm-hmm.
So
So between after you do this, man, this is so annoying. Uh, yeah, I know why. So we need to
memory
add on the
RAM
RAM the literal.
adds 3.
Oh, I think it's this. Yes.
No, I actually wrote it in decimal, but since it's a single digit, it's actually
Yeah,
the
since
same thing. So
yeah, but well, let's just put this then. No problem there. Then after all of them, we are gonna keep doing this. Thank you for being horrible with me. This editor is evil. I gotta say that.
So it's 3, 4, 5, and then 2 and 2. And
How much I
then
miss you, Max.
and then I think when we halt, just for so we can actually see what we're doing, it would be interesting if we log halting. It would also be nice if we logged the I guess just the top of the stack would work, just so we can see that we got the right result. And because the top of the stack, we know in this case is going to be an integer, and we want to make sure it's the right value. Yeah, get a stack, pop, and then integer value. That should work, I think.
I don't need to pop. We can just seek, but well, it's gonna be a pop
Peak,
anyway.
not seek.
Peek. Yeah. Seek. Seek is something else. I'm going crazy.
Uh, yeah, that works, I think.
Uh. Oh, it's a long. So L. Alu. Yes.
Long unsigned. Sure, that works.
Okay, it exploded on our face. Stack empty.
Great, the stack
Cannot
is
pick.
empty.
Wait,
Uh,
did I pick the right one? I picked the data stack.
it is the data stack. Huh, that's unexpected.
Funny that it's right in the beginning. Let's see. Oh, wait a second. We halt here. So at this point, it's empty, indeed.
It shouldn't be because we first call the
Oh, we call.
function
That's true.
at address 3, which should compute a value, and then we halt.
Mm-hmm. Do you need to pack word on those two? No, right? That doesn't make sense.
No, you don't.
Like, I was thinking of just the literal, but that would be an opcode for literal. That's not right. Uh, I don't get it. Why would it be empty?
At peak, and then at peak at line 96, right? Or is that wrong?
It is indeed empty. We have opcodes.
You see fetch, calling, and halting. Why is it not printing the other? Uh, it should have printed the other instructions we are executing, right? Because we are calling a function
Yes.
which has instructions of its own, so it should print those as well. Did we mess up
Should.
function calling somewhere somehow?
Just give me a moment, man. Be right back.
Okay, I'm going to stare at the code and see if I can find a problem in the meantime. Where is my editor? The time. Let me go to the correct branch.
Okay, I'm back.
Welcome back. It's checkout. Oh,
So let me think here. It printed PC fetch first, right?
uh, yes, it should because it's
Yeah.
fetching
Let's
the
get
first
the next
instruction.
word. Yes. Okay. Next instruction. And then calling, which is the first. That is true. But then why does it call halting immediately? I mean, it should have jumped to the 3, right?
It should have, yes.
That's the problem.
Uh, Time VM. Let's see. Evaluate. There's an opcode, which is the one currently executing.
Mm-hmm.
Find in enumerator ISR. Huh.
Why does it call halt afterwards? I don't understand. Hmm. But it's really tough to do this when you are sleepy. Um,
If it's equal to OP halt, OP push. Let's go to OP halt. Value of PC is the integer value of the program counter, and then It pushes the value of PC onto the return stack. And I'm looking at the previous version of the code, but it sets the it sets the PC to the oh wait. Is that correct? Object at index value of PC.
Hmm.
It should be.
Let me think here. Man, I sometimes I feel like I should become Father Brown doing this sort of stuff. Because you gotta go in the realms of psychology to understand. But in this case, it's myself, so it's a self reflection. Okay, so let's see what would be the correct execution here. It would be go to 3,
Uh,
and then 3
uh,
would immediately summon this.
the other one, that's it's zero based, so that's two actually.
Oh, right. So
Three.
0, 1, 2, 3, right?
Right.
So I should call fetch again.
Oh, question is we are doing references using the mutable array vector object thingy, right? Is that actually zero based?
So the question is, oh, okay. So I, if you ask me, okay, how can we test this? Let me think. Do you know easy way to test this? We need to.
Objective immutable array
Okay.
indexing. Apple
Let
documentation.
me see here. I'm getting dizzy already. Uh, fetch, call.
Insert, remove, add. Um,
PC fetch OP. Oh, wait a second. No, man, it's not that. It already gets there empty. Why didn't it insert first? Because there's a OP fetch, right? The fetch should move to the data stack, or am I wrong?
uh, yes, OP fetch should grab the value pointed by the program counter and move it to the data stack. Yes, it
Mm-hmm.
should.
What's going on? Pesky
Um,
bug. So I think it's clear it's not reaching the 3, right? Otherwise it would bring to PC fetch. But the question is, what is the OP fetch doing then? Oh, let's go back to the call. I think that's where the problem might be. Here.
OP call, right. So it checks if we have a program counter, which we do.
Mm-hmm.
It takes the value of the program counter, it pushes to the return stack.
Oh, wait a second. What if it's okay? The enumerator there is just for the registers. That's fine.
Then it pushes the current ISR to the instruction stack, and that's a modification we just did. Then it sets the PC to the value of PC as the index for the RAM. So it goes into RAM, fetches the value, adds the index, whatever the PC was pointing to. Uh,
Man, this is really bizarre. Because I can't think of a reason why. Let me see. So
run run the code again real quick and see what happens, please.
on here, it's gonna blow up because this is empty.
Like PC fetch, calling, and halting. Uh, well, you know what it could be? We never actually initialized the program counter, do we? Let me check that.
Uh huh.
No, we
Mm.
actually do. It's right there in the. No, wait, it's in execute. Yeah, it's in execute. We actually do set the program counter to 0. Mm,
I mean, yes, it is this function, and then we do. Yeah, we do here PC. Yeah.
right, so we set the PC. We clearly managed to fetch the instruction correctly, the first one at least. Because it's printing the calling and then the halting, which is what it does.
Mm-hmm.
And when it prints calling, if finding a numerator and then else is a throw. What happens if you step the code in the debugger?
Wait, to repeat. Sorry.
You are in the debugger currently, right? Can you
Right.
step the code?
I can. It will blow up immediately because of the peak.
It's doing a peak. Why is it doing a peak though? It shouldn't. Oh, right, because it halted and now it's going to print, but it didn't call the function. Why would it not call?
Manin, can we stop here, man? I'm almost sleeping on my chair.
Sure, we can look into this at some other time.
So let's wrap up, and then I'll keep the PR open. If you want to check this tomorrow with me again, if you have the time and will to do it, I'm fine.
Uh, I guess I don't see a problem with that. Just make sure to push this commit
Yeah,
first.
I will. So that's it for today, folks. Sorry, but I am almost sleeping, so I was literally dozing off. So it's better to just go. So, yep.
Yeah.